Yeah. Good afternoon, everyone. Again, this is our lecture 32 in high dimensional probability and applications to data science. Last class, we formulated a problem about community detection in networks. Community detection in networks, where we have a network and we look at it as a graph, and suppose we want to detect some structure in that graph. The most remarkable structure may come from communities, the vertices that are more tightly connected within themselves than to the rest of the world. We proposed a simple mathematical model for network with communities, and that is called stochastic block model, stochastic block model, SBM, where we just model a network as a random graph with n vertices that are split into two parts. Let's call one vertex is boys and the other vertex is girls, let's say. N over 2 vertices here, n over 2 there. And then the edges, which we may interpret as friendships, occur at random between any pair of boys with probability P independently and girls with probability P independently. Boys with girls with probability Q, which is less than P, also independently. All the edges are independent here. So this is G and P. The fact that the fact that Q is less than P means that boys are more likely to be friends with boys and girls more likely to be friends with girls than across themselves. So that's our standing assumption. And now the question is, we get a graph generated from this model, a network generated from this model, but we do not know where the communities are. We would like to build an algorithm that finds these communities as best as possible. And we did that last time. The key to success was spectral properties of the adjacency matrix. So we look at the adjacency matrix A, we look at the eigenvectors, specifically, the first eigenvector will not tell you anything. The second eigenvector will be informative. The second top eigenvector, V2 of A, of the adjacency matrix A. Remember what adjacency matrix, by the way, right? It's just matrix full of zeros and ones. You put a 1 if vertices I and J are connected, and you put a 0 if they're not connected. So it's a matrix that encodes the graph. That's how you present the graph to the computer, actually. So you look at the second eigenvector of the adjacency matrix, and you look at its coefficients, and they cluster. Here's how. Let me show you. You'll see something like this. So some of the coefficients of the second eigenvector, V2 of A, will be positive, and some will be negative, and they will cluster in a very nice way. So we'll just declare this to be community 1, let's say boys, and this community 2, girls. So all these vertices with positive coefficients are boys, and the vertices with negative coefficients, let's say, are girls, or vice versa. We proved that if we look at the coefficients, that they actually predict, they recover the communities with high probability if P and Q are sufficiently different. Well, obviously they have to be sufficiently different, otherwise there is no structure, right? If Q equals P. And so we proved something like this. If you scale P as A over N and Q as B over N, this simply means that every boy has on average A friends among boys and B friends among girls. So if you scale this, and if you require that A minus B is sufficiently different, we did something like this: A plus B log n. We don't need to remember this, but something like that. So if this happens, the separation assumption happens, then everything works. Then there is 99% accuracy, which means that we can make a mistake in maybe 1% of boys and misclassify them as girls and vice versa, but otherwise 99% accuracy with 99% probability. It's a random graph, so it's a probabilistic statement, of course. We proved this using matrix concentration inequalities, matrix Bernstein inequality. Okay, so that was with it last time. Any questions? Remember that? Okay. Good. All right, then this problem is so elegant, so nice. The model is so simple that it attracted a lot of attention in the recent years. And other approaches, other than using, for example, the adjacency metrics, have been proposed, and they actually work better. So other approaches, instead of using the adjacency metrics, you can use something else. And you should know. You should know about these matrices. The first, the most important matrix, maybe other than adjacency, is the graph Laplacian, whose motivation comes from physics. It's dissipation of heat on the graph. It's defined something like this: I minus D minus 1/2, A D minus 1/2, where D is the diagonal matrix with the degrees on the diagonal. And the degrees is just how many friends each vertex has. So you normalize basically by dividing this D to the minus 1/2, you normalize the degrees, and that works well. This is due to Levina and myself in 2017. Graph Laplacian is actually, maybe it's even works better in some applications than adjacency metrics. A very recent work, which is still kind of in progress, is non-backtracking metrics. I'll not define what it is, but it's something like if you walk along the graph and the metrics, you're not so you're required not to backtrack your walk. Then from that walk you reconstruct the metrics, so you can't really go backward. So this is non-backtracking metrics is due to Mosel, who is our speaker on Tuesday actually. Niemann and Sly and Masul. 2015, around the same time. Also, an alternative approach to all of this is to do a semi-definite relaxation, semi-definite programming. If you want to find the two best communities, you want to separate the vertices into two communities, that's a combinatorial problem, right? You just want to, this vertex is a boy and this vertex is a girl. It's like a binary combinatorial problem. And we have studied these combinatorial problems, and we showed how to relax them to semi-definite programming a long time ago in this class. So that approach is also very popular and very useful. It's due to Abe, Bandeira, and Hall. Beautiful work, 2015. Also Gedon and myself, 2016. The advantage of all these approaches, alternative approaches. Why do you need anything else? If the adjacency matrix works well, why are we discussing this? The advantage is they work better sometimes. They remove, all of them are able to remove the log factor. First of all, it's not a big deal, but But for the sake of elegance, you may ask if this is needed, if the log factor is needed. The answer is no. Actually, log factor is not needed there. And here's the state of the art in this. If a plus b, if a minus b squared is less than, and you can actually find the constant that is exactly correct. And this is 2. 2a plus b, then no separation. It's a bad situation, no separation, no method works. This is Marcel, Neumann, and Sly results. No method works means that you can as well just flip a coin and decide who is a boy, who is a girl. No method works in 50 with probability with accuracy more than 50%. But this is a sharp threshold. If you exceed that, if the separation is slightly larger than 2, then there are methods that work with greater than 50% accuracy. Also, Marcel, Neumann, Sly, Masul. So you can then detect communities better than a random guess. And if you allow the constant 2 to grow, c times a plus b, and if c is sufficiently large, then you can achieve any accuracy, for example, 99% accuracy. This is Marcel, Neumann, and Sly. I cited this works up in the previous line. Levin and myself, Gedon and myself. And finally, if you allow a logarithm, if you reinstate the logarithm, I'll put it in this form. This is a sharp one. 2 root log n. Then, surprisingly, it works with 100% of accuracy. Abbe, Bandera, and Hall. 100% accuracy, which means that all of the boys, all of the girls are classified correctly, up to permutation, of course. So this is a state of art as of today. This problem looks like in the recent years, this problem has been completely solved, the community detection problem. Any questions? The fact that some methods in this regime work with 100% accuracy, it looks great, but it also indicates that the model is too simple. Nowhere in this world can you achieve 100% accuracy on realistic data. There will always be outliers. And so that means that the model is simple, and we should be looking beyond the stochastic block model. We should be looking for more realistic models of the data. The first step, and this is what will happen today. We will we'll walk toward more and more realistic models, which unfortunately means that we depart farther and farther from beautiful theory, because the theory is only built now for this very simple model. And then we will go into a completely wild west when so there are some methods that seem to work sometimes and sometimes they don't, and we'll see. So I'll describe all of this work, including the most popular methods for clustering and visualization for practitioners. So the first step, how we depart from stochastic block model with 2 communities toward the more realistic data, is to allow more than 2 communities. Not just boys and girls. Allow more than 2 communities. For example, like this. Let me show you. Something like this. Here is a model with 5 communities. And the stochastic block model is very flexible. Instead of 2 communities, you just define it the same way, right? Separate the clusters, separate the vertices into 5 clusters, and still have them connect the vertices within each cluster with probability p, across clusters with probability Q less than P. So same model, just with more communities. Question is, can we handle it? Yeah, of course we can handle it. Remember, in one community, if there's two communities, what did we do? We look at we look at one eigenvector, second eigenvector, and its coefficients clustered. So some of them are positive and some of them are negative. And we say, okay, this is our boys, this is our girls. So we cluster the coefficients like this. And that was the method, the spectral method. So what do we do now? If there is more than two communities, what do you think? There is no such thing as positive and negative anymore, but what would be the natural generalization for, let's say, if we have three communities? How we should proceed? Any ideas? What would be the dream? Like we have, look at, if there's two communities, we look at one eigenvector. So it's one-dimensional line, and this coefficients cluster like that. Now, if we have 5 communities, what do we do? Or 3 communities. When we look at 3 eigenvectors, and instead of projecting them to one line like this, project them to 3-dimensional, well, maybe 2-dimensional space, and cluster them there. And that's what's happening. Yeah, so now we have 2. We can allow 2, maybe 3 eigenvectors, project everything there, and it should cluster like this. That will be a 3-dimensional picture. And the proof is the same. You can just generalize this proof. So if we have more than 2 communities, then what do? We include more eigenvectors. Of A. For example, 3 eigenvectors. Let me show what it looks for 3 eigenvectors. So we stack them together like this. Let's say V1, V2, V3. So we stack them as 3 columns like that. And then instead of looking at the coefficients of each eigenvector, the coefficients of single eigenvector, we look at the rows of that matrix. Let's call the rows maybe x1, x2, x3, etc., xn. So by doing this, we represent the graph G as a set of points in R3, x1, x2, xn in R3, generally in Rk. So let's say we include k eigenvectors in Rk. So we'll have a picture like this. The proof generalizes and it shows that these things cluster, that these points cluster in R3 or in Rk. And then we can just apply one of the clustering methods, maybe one of the popular clustering method, which is k-means. Or not cluster, or just visualize the graph G. This is a wonderful thing. We have a graph that we cannot imagine because it's very large. And now we have a way to visualize it as a point set in Rn. It's a way to geometrize the graph, to make it geometric. So we can, what we achieved here is we take any graph, in particular stochastic block model, but it applies to any graph, and you can embed it, represent it as a point set in Rk. And this method that we just described is called the spectral embedding. It looks at the spectrum, it computes this k top eigenvectors, and then embeds the graph as the rows of that matrix. Here we go. So we describe the spectral embedding. which works far beyond the stochastic block model or the clustering needs. It's just a method to visualize the graph. And I'll give examples how it works, but this is the thing. Okay, guys, do you understand spectral embedding now? Yeah, just compute the eigenvectors, look at the rows, and they will give you the embedding. Good. Any questions on spectral embedding? Cool. Okay, so we found a way to geometrize the graph to represent them as a set of points, make them a geometric object. Very nice. Actually, there is a way back. Vice versa, we could oppositely, vice versa, we could visualize the set of points, the geometric data, any set of points in RD, let's say, as a graph. We can construct a graph from points. That would be very interesting. How? There are two ways to do this. If we have points like this, like this, what we can do is we can just connect the points that are close to each other, like that. So I'm literally building the graph in real time for you. This is called the neighborhood graph. Yeah. So we can just connect each point xi to its k, let's say capital K, nearest neighbors. Two nearest neighbors, three nearest neighbors, seven realistic. Seven is realistic. Maybe 20 at maximum. So this is called K nearest neighbor graph, KNN. Or a slight variation of this, you can connect xi to xj if, so all points that are close to each other, if xi minus xj is less than epsilon. This graph is called epsilon graph. So either you connect the nearest neighbor, no matter how far or how close the neighbor is, or you just connect the points that are within fixed distance from each other. It's a slight variation of the same idea. Good. Is the definition clear? Yeah. That's how we can compute graph from the point set. And here is how it works. So here's a data set, points, just points in R2. And here we consider KNN graph, just like that. So we construct, what is it? K equals 5. So I can connect each point to 5 nearest. I don't think it's 5. I think it's 3, or maybe 4. I don't know, something like that. Or we can do the epsilon graph, just connect the points that are close to each other. Results are pretty much the same. But why do we want to do this? What is so good about these graphs? Let's look at this. See how the graph captures this structures. It actually already kind of clusters, separates these nice structures from themselves. So the neighborhood graphs, they care about local geometry. They don't care about global geometry. For example, how far this point is from this point. It doesn't really matter. The graphs care about the local geometry, what happens near each point. And therefore, they are able to capture the local shapes, such as this sausage means maybe this sausage, this little blob. And that is what we would like. This is what we would like to uncover, really, in the data. We would like to uncover these hidden patterns, the local shapes, and the graph is able to do that. So that's a very simple idea. Good. So we have achieved two goals already. One of them is that we visualize the graph as a point. We can visualize the graph as a point set. So we embed graph in RK. And the other one is we can embed RK into the graph, the points in RK into the graph, which means, let's just stop and record this. So this is 2 and 3, imply that we have kind of established a two-way street between graph theory and Euclidean geometry. It's called geometric graph theory. There's a marriage between these two. In particular, we can apply these two steps together. We can start from the point set in RD, your genes, for example. And then we construct the graph, the neighborhood graph from them, just like I showed you. Then and then you embed this graph back into RD, or maybe dimension smaller, RK. So this will be by the neighborhood graph. And this will be done by the spectral embedding. So in the middle, we have the graph, but then we'll forget about it. We just have the set of points as an input, set of points as the output, and it passes through the graph in the middle. Why? Because the graph captures the local shapes. That's a problem. So that is one of the methods to visualize or to cluster the data using the neighborhood graph. And here how it works. Yeah, by the way, everything is okay now? Any questions? We're good? Okay, how it works. This is how it works. This is one example. This is from someone else's paper, and this is a population density in the region in Switzerland, in the region of Lausanne. Renault is a suburb of Lausanne, and here is the data. The data is simply the people that live in these different points. What they did first is they just ran the k-means directly on this graph, and the k-means give you something like this. There is one huge cluster and a lot of tiny clusters. So one huge cluster that is orange, like red one, and the others are very tiny. So not very enlightening approach. Then what they did is what I just suggested. They took this data, they took this data, they constructed the neighborhood graph from it, and then they spectrally embed the neighborhood graph back into I don't know, maybe R3, for example, RK, and did the k-means on that. So instead of doing k-means on the original data, they factor it through the neighborhood graph. And this is the result. So this is the result like this. So Lausanne is its own cluster now, and Renault is its own cluster now, which is much better. So that's one simple but very effective trick, which hinges on this two-way street between graph theory and Euclidean geometry, and we can interchange one with the other, basically. Any questions? Yeah. Okay, guys. What will happen next? We'll go farther and farther from theory into more practical applications, but please ask questions. They will help. Okay. Spectral embedding of the graph is only one way to do this. There are other ways to visualize graphs in RK. And one very general way that you probably should know about is an alternative to spectral clustering. It's a very general method that's called multidimensional scaling. Multidimensional scaling, or MDS. In fact, it's very general. It embeds, it's allowed, it embeds any finite metric space. Any finite metric space into any Euclidean space. Okay. By metric space, if you don't know what it is, it's really a set of points with some notion of the distance between them. It could be Euclidean distance, but it could be something else. So it's a finite metric space. M is a set of points. Let's just denote them x1 through xn. They do not need to be points in Rn. They're just abstract things with some notion of distance between them. So for every pair, I specify the distance. Okay. How is it done? It's a super simple idea. It's almost a trivial idea. So these are the distances between the points. And I would like to embed them into Rk. So I would like to represent them as points in Rk. How? Well, I would like to mimic the distances. The best possible situation is that the distance match. So I would like to find points yi's in Rk, which exactly replicate the distances between xi. This will be the best situation. Now, this is not always possible because metric spaces may not be Euclidean. Not always possible. So what we do is we just penalize the difference. I just subtract that. That's my error. Square it, and sum over all pairs. This is a penalty. I would like this penalty to be as small as possible, ideally 0. So what we will do is we will minimize this objective function, minimize the penalty over all configurations of points in Rk. That's it. Done. So this is an optimization problem. You put it in a computer, and computer runs and outputs the set of points in Rk. The advantage of this, of the multidimensional scaling, the pro, is that it is general. The disadvantage is that the objective function is not convex. And so we do not know if it converges, we do not know if it gets stuck in a local minimum or finds a global minimum, and we don't know pretty much anything about it, so there is no theory for multidimensional scaling. Sometimes it works pretty nice. Any questions? MDS?
Is it the same that the t-SNE is doing?
Yeah. t-SNE, yes.
Yeah.
We'll go over t-SNE. It's very similar to t-SNE. The idea for t-SNE comes from multidimensional scaling. Yeah, that's a great idea. We'll get to t-SNE shortly. Yeah, thanks for asking. Okay. Any other questions? Good. So this is the MDS, multidimensional scaling, is super general, right? You just can embed any metric space, anything with this, any kind of notion of distance into Rk. And in particularly, we can embed a graph if we represent a graph as a metric space, and we can do that. Graph as a metric space. All it takes is to define the distance on the graph. And the distance will be, it's called the graph distance. It's the shortest path, the length of the shortest path between the points. So the metric is the graph distance between any pair of vertices. and it's just the length of the shortest path between them. For instance, okay, suppose we have a graph like this. And here are the vertices, 1, 2, 3, 4, 5, 6. This is vertex U, let's say, and this is vertex V. What's the shortest path? Well, there are many paths here. You can walk from U to V in 3 links like this, in 4 links like this, but the shortest one has 2 links like this. And that means that the distance between U and V is 2. So that's graph distance. With it, graph becomes a metric space. And then you can use the multidimensional scaling to embed the graph into RK. Like this. Yeah, what if there's no path? Yeah, what do we do? And if there's no path, means that the graph is disconnected. There are 2 components. Just like, let me show you, maybe like this. Like this. The distance between, let's say, the distance between this point and this point is like maybe 10, that's fine. But what's the distance between this point and this point? There's no path. So it should be like infinity or something like this. Too bad. That's too bad. We don't want situations like this. So what we do in practice, how can we achieve this? Instead of doing the epsilon neighborhood graph, we do k nearest neighbors graph. So we connect each point to its nearest neighbor. And then there's always a path, right? Everything is connected to everything. There's always a path from the neighbor to others. Actually, no, there's not always a path, right? Nearest neighbors can have no paths. No, yeah, it could be still disconnected. Okay, what else can you do? We can, yeah, this is the problem that people actually face. We can add very, very weak links to everything. So we can construct a weighted graph. So this is our graph that's disconnected. And then we add very, very weak links, like put a weight 1/1,000,000 to each link like this between all vertices. That will make it connected, but in a very weak sense. That's another kind of a hack to this problem. And I'm sure the practitioners have other solutions to this. I just don't know. That's a very good question. Any other questions? Okay, so summary so far. We know a way to visualize the graph now. We can either do this by spectral embedding, where we use eigenvectors to do that, or we can do it using multidimensional scaling, which is an optimization problem, like this. Backwards, we can construct graph from the points. We can map RK into the graph, so there is a 2-way links. Putting all this together leads to our first realistic method for visualization of data. That's called Isomap. Have you heard Isomap? Yeah. Isomap. So here's the algorithm. The input is the data in RD. Okay, so what do we do? We first construct a neighborhood graph. Let's say k nearest neighbors, maybe 5 nearest neighbors. So you connect the points that are nearest neighbors. Then we compute the graph distance between all the points xi, xj. It's a non-trivial task, by the way. You can do that. And then we apply the multidimensional scaling for this metric space. And the output will be the set of points. So we apply the multidimensional scaling like this for the graph distance. And we output the resulting set of points. And in our, okay, maybe in R2, for example. And this K maybe, for example, 7. Okay. So this is one of the methods that actually works in practice, and it was suggested by a psychologist, Stanford psychologist, mathematicians in early 2000s. And it is a popular method. Is the setup clear? I'm going to demonstrate how it works in practice now, but is the setup, the description of the algorithm clear? Yeah. Good. All right. Now, see how it works. I'll show you how it works and it'll become crystal clear why we do this. Okay, here's our data. The data is a Swiss roll. This is actually from the original Isomap paper. The data is a Swiss roll. So it's three-dimensional, like a sheet of dough that's curled like this. We construct what's Isomap? All right, we construct the neighborhood graph. We get something like this. So we connect maybe 7 nearest neighbors. We compute the graph distance. And then we let the algorithm work and find the multidimensional scaling. And the MDS shows like this. It unrolls the sheet, the Swiss roll. So the result is the unrolling of this data into R2. Now see how the graph distance here is better than, for example, applying multidimensional scaling to this specific set of points, or maybe projecting this. If you do PCA, for example, PCA will just linearly project it. It will just smash your croissant, your Swiss roll into one flat piece. That's not good. Instead, what this Isomap does, it computes the graph distance. So for example, for these 2 points, the usual Euclidean distance is a straight line, but that's not what we want. The better notion of the distance is the graph distance, which will be this, the length of this curve. And that's because the graph is disconnected here. There is no connection. So it goes through the length of the shortest path, which is this. And that's a natural distance for that Swiss roll. So the graph distance is more natural. And after you apply it, of course, it just unrolls this. Is it clear, by the way, why it should be kind of unrolled or rolled? Because it's isometric, right? The graph distance, imagine I unroll the Swiss roll. The graph distance will still be the same. The graph distance doesn't care about this curvature. When we say the length of the shortest link, the length is, this is 1, and this is 1, and this is 1. Every edge carries weight 1, regardless of its Euclidean distance. So therefore, it's isometrically the same. Yeah. Any questions on Isomap? Cool. All right. So you have one tool that actually works. Unfortunately, there is little theory because MDS, the weak link is MDS. That has no theory. Okay. In MDS, we use the graph distance here and the Euclidean distance here. Instead of doing this, we can do something a little smarter. We can use kernels. We can marry this idea with the kernel trick. So for example, instead of the Euclidean distance, you can put e to the minus Euclidean distance squared. I'll explain why, but let's write up what we mean. The MDS plus the kernel trick gives you another method, which is called SNE. It's kind of an upgrade to this SNE, or stochastic neighborhood, or neighbor, I can't remember, embedding. So here it's the same idea, but we embed the points in Rn. We can embed the points. Let's forget the graph. Actually, the kernel trick will work as we'll replace the graph here. So the goal is to lower the dimension of the data, to visualize the high dimensional data here as a low dimensional data here by solving this MDS problem. So you do the kernels, e to the minus xi minus xj squared over 2 sigma squared. Sigma is just a fixed number, like 7, for example. It's a parameter of the algorithm. The same for y. Yj squared over 2 sigma squared. We would like ideally them be the same. So we'd like to replicate the distances exactly, but that's not possible. So we square the difference, let's say, and we penalize that. That's our penalty over all pairs of points. And we choose the best ones. We choose the best configuration of points yi's. So this is kernel MDS, basically. Why? Right? What does this achieve? Why is this better? If xi and xj are far apart, let's say sigma is 1, just for the sake of clarity, sigma is 1, and xi minus xj are 10 apart. Then, imagine what happens. 10 squared is 100. 100 divided by 2 is 50. E to the minus 50 is near 0. It's near 0. And so what is the best yi's? The best yi's to replicate that will be any set of points that is also far apart. But the point is, it does not matter where apart, how far apart yi's are. As long as xi and xj are, let's say, 10 apart, they will be nicely replicated by any pair that is 5 apart or 10 apart or 100 apart or 1,000. It doesn't really matter, because what we see here is almost 0, and here's 0, and here's almost 0. So yi's do not care about, this method doesn't care about global geometry. As soon as xi and xj are far, it doesn't really matter where they are exactly, right? This only cares about local geometry. So the advantage, the pro, is this method cares about the local geometry only, just like the neighborhood graph. Basically, you can think of this as a smooth cutoff of a neighborhood. The exponential function like this, right? It's a smooth cutoff of the neighborhood. It only cares about what happens here, and then it kind of goes to 0 pretty fast. Then it doesn't really matter. So it tries to mimic what happens within each little neighborhood. And it really doesn't matter what happens elsewhere. For example, if we have a line like this, a curve like this, and the points are on the curve, just like that, then it really doesn't matter how we represent that curve in high dimensions. It could be like this. the penalty is minimal between these two. Is this clear? Because, for example, these 2 points are, let's say, far apart, and it doesn't really matter that we put them even farther. The penalty is low. So what this method achieves, the SNE, what this method achieves is that it cares about local geometry, just like the neighborhood graph. And so we can bypass the graph now. We can just directly apply this method. Any questions about SNE? It's not the best method. I'm going toward t-SNE, and that will be the main competitor. But that's our necessary step toward that. You're quiet today, guys. Ask me questions. Yeah, MD is good? Okay, unfortunately, no theory. SNE, okay. The moment we represent this as e to the minus something squared over 2 sigma squared, it reminds us of probability. Right? This looks like probabilities. This looks like Pij, and this looks like Qij. The probabilities for the normal distribution. So we can look at this method geometrically. We can consider the probabilistic view of Pij and Qij as probabilities. Okay, there is a little technical issue that you have to normalize them, that the sum of Pij's and the sum of Qij's, if they are real probabilities, they need to sum to 1. So we need to normalize within the algorithm, but let's forget about that issue. So we are trying to, so if we look at this as probabilities, we're looking at this as a stochastic model, a probability model. And we would like the stochastic model for the true data be close to the stochastic model for the low dimensional representation. We would like to match the two stochastic models, the two distributions. And this is not the best way to match these two distributions, just the least squares. There is another function that captures the difference between the two distributions. And that's called the relative entropy, or the KL divergence. Kullback-Leibniz divergence, also known as relative entropy. And is defined the following way. The divergence between two distributions, P and Q, is Pij log Pij over Qij. Guys, have you heard about KL divergence before? Yeah. So what we did before, we said let's do Pij minus Qij squared, and that's a multidimensional scaling objective function. And now we're saying no, this is not so good. If you look at Pij and Qij as probabilities, we should genuinely try to match the probabilistic model, and KL divergence is a very good thing to do. Why? Let me say it in words. So heuristically, the KL divergence means this. This is our true data. This is our model of the data, something that we impose on the data. And heuristically, KL, P versus Q, is the amount of information in the true data, P. that is not explained by the model Q. We can make the statement rigorous. This is Shannon theorem. That measures the amount of information as a number of bits. I will not go into that direction because this is information theory, but it's a beautiful theorem. You should take a look at it. The point is that we are doing exactly the same. Here, PIJs are the distances between the true data. QIJs are the distances between the model that we put on the data. We look at them as probabilities, and we would like the model to explain the true data, right? We would like the low-dimensional representation, low-dimensional image to explain the data, the high-dimensional image. And the good objective function for that is KL divergence, because that measures the amount of information that is not explained. Great. So what do we do? We just minimize. We just minimize KL PQ over all points in our K. We find the best configuration of points that best explains the high-dimensional data. Good. That's SNE. Any questions on SNE? Good. Recently, 2008, 2010, something like that, people realized that if we make one little adjustment to this model, then it would perform amazingly well. And that is, instead of the Gaussian model in low dimensions, this e to the minus something, just put the Cauchy distribution, which has heavier tails, and that becomes t-SNE, the main competitor and currently the most popular practical method to visualize the high-dimensional data. So this is t-SNE. So instead, in the low-dimensional space, instead of the Gaussian distribution, use the Cauchy distribution, which has heavier tails, and therefore it's a little more forgiving for the outliers in low dimensions. So Pij will be as before, they're Gaussian. But Qij's will be Cauchy, and Cauchy is this distribution, yi minus yj squared. And then we just minimize, just as before. Just minimize, find the best configuration of low-dimensional points in Rk. And that's t-SNE, that's it. That's a vanilla version of t-SNE. Which at this point is probably the most popular method to visualize the high-dimensional data. In a moment, I'll just show how it works in practice, but any questions on the setup? Good. Try it yourself. It's super cool. If you didn't already. Okay, t-SNE, how it works. Let's see. All right. Now experiments. This is a benchmark data set in machine learning. It's called MNIST data set. It's a set of handwritten digits, just like this. Zeros and ones and twos, different people write them differently. And this is our data as images. I'll show you three examples, three methods. First is just PCA. PCA, remember, it projects everything onto, let's say, two top eigenvectors, just a linear projection of this, it works like this. It does identify some structure here. This is the 4s, and this is the 0s, and this is 5s, and so on and so forth. That's PCA. The next one is Isomap. It does things a little bit better. Isomap. So this, for example, is a zero, the handwritten zeros, and this is 9s, and this is 3s, and so on and so forth. Also very nice. This is 1s. And this third one will be t-SNE, and t-SNE does like this, which is even better. I think all the 6s, except a couple outliers, are clustered together, and all the 0s are clustered together, and so on and so forth. So that's t-SNE. This is from the original paper. Okay, second experiment. Another benchmark model is a COIL dataset, COIL 20 dataset. These are images of rotated objects. We just have one duck, let's say, we put it on a rotating platform, and we capture the images of it as it rotates every 5 seconds, or every 5 degrees, I think. So this is, for example, the set of images for one, I don't know who this is, a cat maybe, as cat rotates. And we do this for each image. Okay, this is Isomap. And you, by the way, it's not clear that any low dimensional representation would give you something like this, like circles, right? Rotation does not correspond to rotation in low dimensional space, but Isomap really does a good job. This is rotation of a cat, and this is maybe rotation of a car or something like this. All right, this is t-SNE. t-SNE is a little bit better. The cat rotates like this, and maybe the car rotates like this, and so on and so forth. And there are some funny shapes that I don't know what they are. Okay, any questions? Good. Okay, how do we practically solve this? Is we how do we practically minimize the KL divergence like this? Is we take the derivative and do the steepest descent. So it's called gradient descent. When you write the gradient descent, you can get inspired by the gradient descent and say, hey, instead of this gradient descent, let me find another formula, and maybe it'll work better. And this is what people did. And the last method that is kind of controversial, but I would like to mention it anyway, is UMAP. That's another main competitor of t-SNE at this point, and also used in many applications, UMAP. This is pretty recent, 2018 or something like this. Have you heard UMAP? No? Well, anyway, yeah, check it out.
Yes.
Yeah, good, Jana, good. So, okay, one experiment will be done. 2 experiments, actually. Okay, here is UMAP. I'll not say exactly what UMAP does. It's a little complicated, but the idea is simple. You just set up this gradient in a nice way. This is digits, MNIST data. So these are 0. These are, oh, where did it go? Sorry, guys, let me find it again. Yeah, this is 0s, and this is 6, I think. This is 3, this is 9, and so on and so forth. So better cluster a little bit. This is COIL data. Definitely better than t-SNE did. So this rotated cats and images of cats and dogs, they're really shown as rotations, as like loops here. Finally, they did this crazy experiment that I would like to show you. The crazy experiment is about what do numbers look like. So you take numbers from 1 to 1,000,000 and represent these numbers as a binary string. Binary string that just tells us what are the prime factors of this number. Let's say I take a number 110, and I will just put 1s for each prime factor of 110, and 0 if it doesn't have a prime factor. So for example, 110 is not divisible by 7, so I put a 0. It is divisible by 1, so I put 1 here. It's not divisible by 13, so I put a 0. So we represent every number, every integer, as a binary string. This way, just prime divisibility. And we put it in UMAP. And this is the first million digits visualized by UMAP. This looks super cool. Nobody knows what it is really. It looks like a galaxy, a universe with galaxies and all these twirls and spirals and the core. No one has any faint idea about what this really means. There is some disappointment. I heard that some people discuss over Twitter that actually this is an artifact of the method. That in fact the structures are not real, and just UMAP is imagining in its own twisted brain these structures. They're not actually real. I do not know if that's true, but that indicates a weakness of generally this methods and the need for theory. Let me just say, in the very last moment, we need theory for this or other methods. Why? Because here we go. You know, people find these galaxies and structures, and then we do not know if they're real. And come on, what is this world? We do not even know if that's true, or the method is imagining this. The algorithm is imagining it. Of course, if we train the algorithm that it must discover some structures, and there is a confirmation bias, the algorithm will eventually discover you some structures. Will it discover it, or will it create the structures? We do not know. For that, we need theory, and we do not have it. We don't even know what is a good visualization. How do we set up? What's a good visualization? How do we define this mathematically? Is there a best visualization? What are clusters? How do we define clusters? How many clusters are there? I give you a data and I ask you if there is 9 or 11 clusters. Very important question in cancer research, in cell differentiation. They want to know if this is a real new type of cancer that's represented by cluster, or this is an imagination. So that's very important. And we don't know. Sorry, I went over time today, but I wanted you to learn about this modern methods, and here we are now at the very forefront of what's known today. Any questions? You're quiet today, guys. What's going on? Okay. Good. Okay, you know Tuesday, it's our meeting with Manuel, with Elkanan Mosel. Please come. And we will see you otherwise on Friday. And if Tatiana, can we meet with you today? Is it possible?
Yes, sure. It's a pleasure.
Great. Okay. Let's meet with Tatiana. Stay on call, and everybody else have a wonderful day, unless you have any questions on this.
Thank you. Goodbye.
Thank you, Dmitry. Bye-bye.
Thank you. Goodbye.
Thank you. Bye-bye, guys. I'll see you.
Thank you. Goodbye.
Stop recording.